Okay, we're going to start 14.5, which is the chain rule in several variables. So first, let's recall the chain rule in one variable. And so let's say we have a function f of t, and we have a function g of t, and we want to take the derivative of f of g of t. Then this is f prime at g of t times g prime of t. So this is essentially the chain rule in one variable. In two variables, this is going to be the situation where we have a function f of x and y, and x is going to be a function of t. Let's call it x is some x of t, and y is a function of t. So we have a diagram that looks something like this. F depends on x and y, and x depends on t, and y depends on t. And what we want is to take d by dt of f of x of t comma y of t. This is the condition. And what essentially is going to happen is, I'll just tell you what it comes out to be. We end up with del f del x at x of t y of t, and then we have x prime of t, which is dx dt at whatever t value, plus del f del y at y of t, x of t first, then y of t, times dy dt. Or suppressing all the variables, we simply have del f del x dx dt plus del f del y dy dt. This is the chain rule, the most essential form of it. And kind of one way to remember it is to just say, okay, let me go down all the columns that connect to t. So for example, this t at the bottom right here connects to x, and that connects to f. And so this, essentially that means I have this derivative, which is a partial f with respect to x, and then there's this derivative, which is dx dt, and these are multiplied. When you go down a column, you multiply. And then you go down the next column. The next column is, the first one is del f del y. Oops, I have a del here, not a d. Del f del y. And then I have a dy dt. And what I do is, between separate columns, I add. So in between, I add. So I have multiplication going down each column. But then separate columns I add. So that results in exactly what we have right here. So let me just state it one more time. So suppose f of xy is given, and there are functions x of t, y of t. Again, we have to assume everything is in the respective domains and all of that, but assuming everything works out, then d by dt of f of x of t, y of t, this is equal to del f del x dx dt plus del f del y dy dt. So this is the chain rule in several variables. There are some other versions, but those are all essentially conditional upon this. This is the most basic one. And how do you show this? So the proof is, I'm not really going to show it, but the proof requires what's called a formal definition of differentiability. Formal definition of differentiability. Which essentially, I'm not going to state it very formally, but essentially it says you can write the function f of xy. So if f is going to be differentiable, so f is differentiable at some x naught y naught, if you can write the original function as the linear approximation, which we saw in last video. And of course, for that, the requirement is implicit that the partial derivatives exist. But actually, just the partial derivatives existing, unfortunately, is not enough to imply total differentiability, which is kind of a subtle point. We won't get into that. But the original function, is equal to the linear approximation. So this piece is your linear approximation, and plus some error term, e of xy. And this e of xy has to satisfy some properties where it goes to 0 faster than the length of the vector from xy to x0, y0. So so there's some conditions here. So there are some conditions where this has to go to 0 as the length of x minus x naught goes to 0. So there's some relationships there, which I'm not stating that in its full form, but you use this to, so we use the proof. So the proof of chain rule uses this, where we plug in, essentially we plug in x of t, y of t, and we take the derivative with respect to, at some particular t value, t naught. So you plug those in and you essentially take the limit as t goes to t naught and see what happens. That's essentially what the process is, and what you end up with is that the e of x term, so the outcome, is that the e of x of t, y of t term, this term, when all gets done, this term goes to 0, and what's left is on the left side. So you have f of x of t, y of t minus f of x of t naught, y of t naught divided by t minus t naught. This is essentially your d by dt of, oops, yeah, that's correct, of f of x of t, y of t at t equals t naught. And this is equal to, the first term you end up with is, you have your del f del x, and that's at x of t naught, y of t naught. And here, when you end up, we divide everything, oops, not z, but x, we divide everything. We'll end up with x of t minus x of t naught, t minus t naught. This piece ends up being the x prime of t naught. This piece is, of course, the del f del x term. And the next term is the del f del y term at x of t naught, y of t naught. And then you have a y of t minus y of t naught divided by t minus t naught. This term goes to y prime of t naught. And so you end up from this overall that d by d, to get the formula, as I stated earlier, that this is equal to del f del x dx dt plus del f del y dy dt. I know I didn't do a lot of detail there, and I probably threw out some terms that were a bit ambiguous. I apologize for that, but I just want you to know that there is the formal definition of differentiability involves something extra beyond what we stated, and that term goes to 0, leaving us with exactly what we stated a bit earlier for the chain rule. Okay, so this is the chain rule, and let's just do one example and leave you with a little exercise. So let's do an example here. So let's say f of xy is x squared y plus 1 over x times y squared. And we have x of t being t squared plus 1, and y of t being t cubed. And we want to find, in general, d by dt of f of x of t, y of t. And we also want to find it at a particular point, say t is equal to 1. Okay, so first we want to find, so we essentially want to find two things. The general form of the derivative of f of x of t, y of t, and then at t equals 1. And we're going to use the chain rule, using the chain rule. Okay, so what is d by dt of f of xy? Or sorry, not f of xy, but f of x of t, y of t. X of t, y of t. This is del f del x at x of t, y of t, dx dt, plus del f del y at x of t, y of t, dy dt. This is the chain rule. So we want to use the chain rule. It's possible to do this problem, of course, without using the chain rule, which would just be to first plug in the x and the y into f. You get a single variable function in t, and then just take the derivative. There are reasons for which that's not always the optimal way. In this case, it might be actually easier, but just for the sake of, we're going to go ahead and do this the chain rule way. So let's go ahead and do that. So let's compute del f del x right here. Del f del x, this is 2xy plus, and we have 1 over y squared, which is constant, times d by dx of 1 over x. So this is 2xy plus 1 over y squared, and here we have negative 1 over x squared. So we end up with 2xy minus 1 over x squared y squared. That is the partial of f with respect to x. And now we want to plug in x of t and y of t. So this is equal to, and I'm not going to simplify completely because we're going to essentially plug in t equals 1 in a little bit. So we get t squared plus 1 t cubed minus 1 over t squared plus 1 squared, and then t cubed squared is t to the 6th. Let me just write that as t to the 6th. So that is del f del, this term is that guy. And then there's dx dt. So dx dt, maybe let's just write it here. X prime of t is dx dt, that's just 2t. Y prime of t is 3t squared. Then there's the del f del y term. So we also want to compute del f del y. Let me do that off to the right here. A little extra column. We have del f del y being x squared plus, and again the 1 over x is just a constant, so we take the derivative of 1 over y squared, which is negative 2 over y cubed. And so we end up with this x squared minus 2 over x y cubed, which when we plug in the x of t, y of t, so again, we're now computing this x of t, y, plugging del f del y at x of t, y of t, we get t squared plus 1 squared minus 2 over t squared plus 1, and then y was t cubed, which when I cube, I get t to the 9th. Okay, so overall, if I had to write this in its full glory, so d by dt of f of x of t, y of t, this is equal to, we have 2t cubed times t squared plus 1 minus 1 over t to the 6th times t squared plus 1 squared multiplied by dx dt, which is just 2t. And then we have plus the next derivative, del f del y at x of t, y of t is t squared plus 1 squared minus 2 divided by t to the 9th times t squared plus 1 times dy dt, which was 3t squared. So this is the overall derivative of, let me just kind of underline this. This is equal to d by dt of f of x of t, y of t, and now we just plug in t equals 1. So at t equals 1, what do we get? We get 2 times 2 minus 1 over, we get 2 minus 1/4 here, times 2, plus, and then in the next term we get 1 plus 1 squared is 4, minus 2 over 2, and then times 3. So we have 4 minus 1/4, so 4, well, everything's multiplied by 2, so let's distribute. We have 8 minus 1/2 plus 4 minus 1 is 3. 3 times 3 is 9. So this is 17 minus 1/2, which is 33 over 2. Okay, so that is an example of the chain rule in several variables. Let me leave you here with a little exercise. So suppose f of xy is sine of xy, and x of t is t squared, y of t is t, and we want to find d by dt of f of x of t, y of t, and the general form. And then we want to find, and let's again use the chain rule here. It's not, again, a problem that necessarily in this case requires it, but let's use it just for practice.